Hi everyone. So in this video, I shall give an intuitive idea about dispersion relation in a long array of diatomic linear lattice. Okay. So in a diatomic lattice, we have assumed that we have two atoms. One is having mass capital M and other is having mass small m. We have designated mass capital M as 2y(n) and mass of capital and mass of small m as 2y(n) plus 1. So now, as we know that in a lattice, due to thermal agitation, the atoms do vibration about their mean position. So likewise in this case also, this atom capital M will do vibration, will do to and fro vibration about its mean position, and due to this mass capital M will experience some force due to its two neighboring atoms of smaller mass small m. Now in this case we have assumed that the individual atoms is attached by a spring. Of course, in actual lattice there is no spring. It is for our simplicity we have assumed that the constituent atoms is being connected by a spring. In this case, beta is the spring constant and x is the displacement of the atom from its equilibrium position. So due to lattice vibration, the atom will get displaced from its equilibrium position, and due to this the atom shall experience a force. In this case we have written two forces. The force on mth particle is given by m u double dot twice n. Here u twice n is the displacement of twice n in atom from its equilibrium position, and u twice n plus 1 is the displacement of this smaller mass. So now if we solve these two differential equation, then this is the solution. Here a and b are the amplitude of the bigger mass m and smaller mass small m. Of course these two amplitudes can't be zero, so we have to form a determinant by taking the coefficients of a and b, and if we equate that determinant to 0, we get a dispersion relation for diatomic lattice. So this equation is the dispersion relation for diatomic lattice. Here omega is the angular frequency and k is the wave vector. Now, as you can see from the above equation, that we have two values of omega, one for plus and one for minus. If you can remember that in a monatomic lattice vibration we have only single value of omega, but in case of diatomic lattice vibration we have two values of omega, one for plus and one for minus. So if you look closely to the above equation, you can see that here beta is constant for a particular spring, capital M and small m are constant, which are nothing but the mass of the two distinct atoms, but the value of A is variable. Also A is constant. Here A is the distance between two consecutive atoms. So here A is the distance between two consecutive atoms. This equation is basically for the dispersion relation. So this equation is called the dispersion relation, and we have two values of omega, one for omega plus and one for omega minus. So if we plot the above dispersion relation, taking omega along y-axis and A along x-axis, we find that we get two branches. The branches which I made from blue line is called optical branch, and the branch which I made from the violet line are called acoustical branch. Now, if you have studied Diatomic Lattice vibration, you are well familiar with this acoustical branch, but this branch is introduced in the dispersion relation of an atomic lattice. The maximum value of the optical branch is given by y beta 1 by m plus 1 by m of whole to the power half. This is the maximum value of omega plus, that is its optical branch, while the maximum value of acoustical branch is root over twice beta by m. And the interesting thing about the graph is that these are the allowed frequencies in lattice vibration, which means that if we strike a crystal with an electromagnetic wave such as light, this range of frequency is allowed for the vibration. Likewise, if we strike a crystal with a sound, then this part of frequency is allowed, but in both the cases this part is not allowed. So this is called the forbidden region. This region is called the forbidden region. In this frequency band, no vibration is allowed. So this region is called forbidden end. So now the question arises that what is the utility of dispersion relation? So with the help of dispersion relation, we can calculate that what are the maximum possible end of frequency in any lattice vibration. Also, we can calculate the group velocity and the phase velocity. We know that the phase velocity is represented as Vp. It is nothing but omega by k, where omega is the angular frequency and k is the wave vector. Also we know the group velocity is d omega by dk. So with the help of this dispersion relation graph, we can easily calculate the group velocity and phase velocity of a particle. Also, we can easily calculate the forbidden end of frequency in any lattice vibration. So, this type of graph, this type of dispersion relation is very important to analyze crystal dynamics. To analyze crystal dynamics. And here the range of A is, it is from minus I by 2ic to I by 2ic. So this range is called the first L1 zone. Similarly, if we go to minus I by A to plus I by A, we get second L1 zone. So this is all about the dispersion relation for diatomic lattice. Thank you.